Enterprises worldwide are currently deploying artificial intelligence systems across their critical infrastructure at absolute maximum speed and scale. But as this financial diagram shows, there is a massive discrepancy. Despite the volume of enterprise adoption, the global AI liability insurance market is $0. Not small, zero. Actuaries write premiums based on probability and predictability. They cannot price the risk of an entity that frequently hallucinates and continuously drifts from its authorized baseline. We have seen this exact bottleneck before. A decade ago, cyber insurance was considered an uninsurable risk. That changed when carriers acquired the tools to physically measure network risk. Between 2015 and 2025, the cyber insurance market scaled from $2 billion to $14 billion. Insurance follows measurement. Right now, the AI industry relies on multi-billion-dollar software patches to manage safety. Engineers deploy RAG filters and use reinforcement learning from human feedback, or RLHF, to rein in erratic models. These patches are designed to evaluate and filter output quality. They do not verify the physical integrity of the AI model's operating substrate. Insurance carriers do not underwrite based on probabilistic software confidence scores. They require rigid, mathematically proven telemetry. They need the exact equivalent of an OBD2 diagnostic reading, but for AI. The industry is stuck in a loop. We are trying to verify software by writing more software. This creates an engineering paradox where true, objective measurement is impossible. Until the verification process is removed from the software layer and executed entirely in physical silicon, AI liability cannot be priced. Every piece of enterprise verification software is, ultimately, just a set of instructions running on a physical processor. It shares the same hardware space as the data it is trying to verify. This diagram outlines the standard industry software verification pipeline. It is a sequential, 7-step computational process. The system must first load the data from a memory address and calculate an expected cryptographic hash. Next, it loads a stored baseline hash from a separate location and runs a comparison operation to check for drift or displacement. Finally, the software branches the decision path to handle any exception and trigger an error alert if those hashes do outmatch. Executing all 7 instructions takes microseconds to milliseconds. Even on a modern CPU, this entire process takes roughly 5 milliseconds. That 5 milliseconds is a blind spot. It acts as a vulnerability window where silent displacement can occur between the fetch operation and the verification check. During that window, the checking software is running on the exact same substrate it is auditing. Because they share a physical environment, the security checker is exposed to the exact same displacement events it is designed to catch. The checker itself can drift. Alan Turing isolated this specific computational paradox in 1936. Turing proved that if a checking program can drift, you need a second checker to verify the first checker. Then you need a third to check the second. It creates an infinite regress. Any software-based compliance tool is caught in this loop. It provides an illusion of security, which means the data it generates is completely void to an actuary. To break the regress, we have to bypass software entirely and look at the physical geometry of the silicon. This diagram compares the 7-step pipeline to a strict hardware alternative, a single atomic instruction called compare and swap, or CAS. CAS relies on a physical reality.
On the silicon layer, the exact geometric coordinate of data serves as its absolute identity. Finding the data at its assigned physical coordinate instantly verifies that it has not been displaced. This executes in a single L1 cache access cycle, roughly 5 nanoseconds on a standard core. The fetch and the verify are fused into one indivisible physical event. This atomic operation reduces the vulnerability window from 5 milliseconds to exactly 0 nanoseconds. There is no time gap between reading the data and checking it. Therefore, displacement during the operation is physically impossible. If correct data ends up in the wrong physical location, it creates an immediate cache miss on the hardware layer. The error is logged instantly. Executing this geometric check generates a mathematically proven, unforgeable cryptographic artifact. This artifact is a rigid tuple containing 3 points, a structural certainty ratio, a tamper-proof timestamp, and the absolute hardware verification outcome. This tuple is the exact enterprise equivalent of a vehicle's OBD2 reading.
It comes directly from the engine, not from a software self-report. By utilizing physical hardware geometry, the system sidesteps Turing's infinite regress. It produces the hard actuarial primitive required to finally underwrite AI risk. This hardware mechanism arrives exactly as macro policy shifts. The European Union AI Act goes into full enforcement on August 2, 2026. Article 14 of the Act issues a specific demand. Every high-risk AI deployment within the EU must possess the ability to correctly interpret output, which legally necessitates independent verification. The word independent has a strict legal standard. The auditing mechanism cannot share failure modes with the system it is checking. This comparison table evaluates current industry tools against the Article 14 mandate. Vector databases, RAG filters, and RLHF all fail the independence test. They fail because they are software living on the exact same physical chip as the AI. They share identical vulnerability profiles. The hardware-level CAS patent clears the standard because it operates on a completely distinct physical layer. As of early 2026, this precise hardware telemetry is the only filed mechanism worldwide that fully satisfies the independence requirement. The EU AI Act effectively outlaws software-only verification for critical infrastructure. It creates forced demand, legally mandating a global enterprise migration to hardware-level compliance. The physical deployment strategy relies on open-source engineering. Operators can build and deploy sub-C Genesis node compute pods freely, using open hardware blueprints. The value isn't locked in the hardware shell. It is generated by the FIM trust layer firmware installed on the bare metal nodes. This financial summary card shows the core unit economics. The business model is driven by an annual $120,000 firmware license fee per node. Because the same firmware binary is deployed across the entire fleet, the licensing model scales linearly, while marginal costs sit at zero. For facility operators, the ROI is extremely direct. The firmware layer transforms standard bare metal co-location spaces into high-premium, completely insurable assets. This telemetry gives an insurance carrier the exact actuarial data they need to write the first real premium table for AI liability, entirely avoiding software guesswork. By linking physical CPU architecture directly to strict regulatory compliance, this entire system opens the multi-billion-dollar AI liability market, driven purely by a highly scalable, zero-inventory licensing engine.